Welcome to today's webcast series presentation, Stormwater Storage Facility and Rainwater Harvesting, a community partnership. My name is Bob Drake, editor of Civil and Structural Engineer magazine, published by Zweig Group, and I will moderate today's session. Thank you for joining this webcast, which is sponsored by StormTrap. The views of the speakers and organizations participating in this webcast are their own, and do not necessarily reflect those of Civil and Structural Engineer or its publisher, Zweig Group. If you have any technical difficulties while viewing this webcast, please submit questions or a brief explanation of your technical problem using the Ask a Question box on the left side of the webcast dashboard, and a representative will assist you. Note the button in the upper right corner to enlarge the slide viewing window if desired. During the webcast, you also can submit questions to our speakers using the same Ask a Question box. Submit your question at any time, and we will try to answer as many as we can later in the webcast. Zweig Group encourages group learning for our events. If you are viewing the live webcast with a group on one registered person's computer, that person must complete and submit the multiple viewer registration form for the group in order for everyone to earn credit. Download the multiple viewer registration form from the event resources on the left side of the webcast dashboard. Submission instructions are on the form. Also note a link in the event resources section to download a PDF of the slides in today's webcast, as well as some other resources. Details on downloading a certificate of completion will be provided later in the webcast. And viewers of archived webcasts must pass a quiz in order to download a certificate of completion. Additionally, at the end of today's event, we will provide a webcast evaluation survey for you to submit your feedback. Today's presenters are Paul Siegfried, Assistant Water Resources Department Manager for Baxter Woodman, and Kelly Hamill, Director of Public Works for the Village of Northbrook, Illinois. Before we get into the presentation today, there's a couple of poll questions we'd like to get your response to. Are you designing a stormwater management system currently or in the near future? You can use the drop-down list to respond either yes or no. Wait just a few seconds. Next question. How many underground stormwater detention infiltration systems have you specified in the last year? And the last question. In the last year, how many projects have you worked on that utilized a manufactured water quality device? So let's get into today's presentation. To get started, Kelly will take over.
Thank you, Bob. Today we're going to be talking about the Wescott Park Stormwater Management Project. This project is owned by the Village of Northbrook and the Northbrook Park District. It is important to note that those are two separate taxing districts with separate elected boards. Baxter Woodman provided the design services and construction oversight for the project. V3 companies built the project, and it's of course located here in Northbrook, Illinois on Wescott Park, which is owned by the Park District. This project included stormwater storage and rainwater harvesting system. The Village of Northbrook is located in Cook County, Illinois. We have a population of roughly 33,170, 13 square miles and 25 miles northwest of Chicago. The Village of Northbrook is known for great schools, spectacular parks and programs, and a high level of municipal services to our residents and businesses. Unfortunately, sometimes a good master stormwater management plan requires flooding. The Village of Northbrook is no different in that case. In 1982 and 87, we experienced quite a bit of flooding with 6.5 and 7 3/4-inch events during those times. In 1987, roughly 818 properties, or 1 out of 12 properties within the village, experienced some type of flood damage which required special debris pickup. With that, our first stormwater plan was created in 1993. It also created the Stormwater Management Commission, which provided oversight of all stormwater-related issues within the village. They were reviewing the causes of flooding, projects to reduce the flooding, and property protection programs. In 1996 and 2002, the program plan was updated for current cost and completion of projects. After that, we had 2 more significant rainfall events, one in 2008 with roughly 6.5 inches of rain, and another in 2011 with 5 1/4 inches of rain. This really put a focus back on stormwater, and that we'd only completed roughly 9 projects since the inception of the plan, and stormwater still was a village-wide issue. The 2011 update identified that some of the past projects were either too large or unbuildable. The new plan would address larger watershed projects, smaller neighborhood projects, and private property cost share projects and education. This new plan was completed in 2011, had roughly 22 projects, 14 were new projects, 8 were ones that were previously identified. It was again updated in 2012 and 2015, bringing the total number of projects up to 31 for our plan. In 2012, the village created a stormwater sewer fund for storm sewer operation and maintenance, construction of these projects, and the funding is provided by a stormwater user fee. Since 2012, the village has completed roughly 11 projects at an estimated value of $18 million. There's 20 projects remaining with an estimated value of $13 million to complete. One project included in the master stormwater plan was the detention facility at Wescott Park, shown above in the red. That was within the Sunset Field subdivision. This is one of our larger watershed projects, and it stood out from the rest because this was an area that we had previously identified projects that were unbuildable. It was the most expensive project within the plan. It provided a large open space in the red area there, owned by the Park District and the school district for potential surface detention. It could provide a large relief for properties in the neighborhood. With the watershed project, it also provided benefit to downstream people that receive flooding, and also would allow the building of 3 other future neighborhood projects once it was completed. As mentioned, there's been past flooding issues in this area along Wescott Park by Farnsworth Lane and some of the surrounding streets. Unfortunately, during flooding events, 2 to 3 blocks are impassable for our emergency vehicles. Sunset Field Subdivision is an older subdivision. It was platted in the 1950s, built without any detention, and undersized storm sewers to compare to today's standards. The only real open space available in this neighborhood is at Wescott Park. So during the study phase of the project, we knew that the Master Stormwater Plan project was feasible for Wescott Park. Unfortunately, we wanted to make sure we refined the project due to the potential cost and the need for the interjurisdictional cooperation, since the village does not own any of the land that the detention we built on. The area in red on the slide shows the extent of the flooding prior to the project, and there are roughly 10 structures that experience flooding during a 25-year event, and roughly 83 properties that have some type of flooding during these events. During the study period, the village retained Baxter and Woodman to provide an evaluation to refine the project details prior to going to design. One of the things that they looked at was the different surface detention that could be provided, underground detention, and also a hybrid combination of the two. These different options were presented and discussed with both the Park District and the school district to try to identify a project which was agreeable to them because it needed to be buildable, especially since it was going to be on their property and not the village's. At the end of the study phase, this graphic you see right in front of you now is where the proposed detention location would be and the proposed sewer route. The village would have preferred a configuration which allowed surface detention, but unfortunately we had to keep the detention located on the Park District property, and that's the hashed area that you see with the proposed detention identification. We also had to keep a portion of that south ball field playable during construction as well. The 23 acre-feet storage is entirely on the Park District property, and the other storm sewer infrastructure improvements are within the village's right-of-way. At the conclusion of the project, using XP Swim, the results you see in blue are the impacted areas of inundation after the project would be complete. It does provide 25-year level protection for all homes. The 10 homes were completely eliminated from flooding during the 10-year event that had prior flooding. And like I mentioned, there was also 83 other homes that saw some benefit from the project as well. One of the key components, while we didn't eliminate all flooding, the emergency vehicles do have the ability to pass these areas during flooding events. At the end of this phase, Baxter Woodman identified an opportunity to store and reuse stormwater for irrigation of the ball field and a possible partnership with Metropolitan Water Reclamation District of Greater Chicago, or MWRD. Due to the coordination that was involved, prior to going to full design, the village worked with Wescott Elementary School and the Park District to set up the ground rules for the design process. We wanted to make sure that everybody was on board with the parameters so that any future changes could be avoided and costly changes to design as well. Some of the things that were identified were the defining the construction limits. As previously mentioned, the south ball field needed to be playable throughout the construction for not only the school's use but the Park District's as well. We had a 9-month construction schedule because the north ball field, which the Park District regularly programmed, would be out of use for roughly one whole season, so we had to get that done so it would be used the next year. It also identified issues with traffic for the school drop-off and pickup due to the large amount of truck traffic that would be generated with the project as well. It also identified that the village would be installing an irrigation system for the ball fields, which would be owned by the Park District in the future. During the design phase, the village did enter into a formal intergovernmental agreement with the Park District to finalize the details of the agreements. As previously mentioned, the village had an opportunity with MWRD to build a rainwater harvesting system for this project. The village's master stormwater management plan had identified other best management practices that could be used with our stormwater plan, but nothing to this scale. The village and MWRD have worked on multiple other projects together, but none of them with really a green component. So the village and MWRD were really excited about the rainwater harvesting component of this project, and it would be a showcase project not only for them, but as the village as well. We did enter into an intergovernmental agreement with the Water Reclamation District for an intergovernmental agreement for their cost participation and funding of the rainwater harvesting system. Prior to turning it over to Paul, I would just like to recognize the jurisdictional cooperation that was needed for this project between the village, MWRD, the school district, and in particular Northbrook Park District, because without them, this project wouldn't have been possible. With that, I would like to hand it off to Paul, and he will speak more about the design and construction of the project. Thank you. Paul?
Thank you, Kelly. As Kelly mentioned, the village ultimately chose the underground detention option, and Baxter Woodman was authorized to begin final design in the fall of 2014. The total cost of the project was estimated to be about $10.3 million without rainwater harvesting, which would only be included if grant funding became available to cover the additional cost. The main components of the design were a 23-acre-foot underground detention facility, 3 blocks of new 42-inch diameter sewer to convey stormwater to the storage vault, constructed in parallel to an existing 42-inch sewer, high-capacity inlets to capture roadway flows, a restrictor to limit downstream discharges, and an irrigation system to water the ball field. Once the underground detention option was decided on, the first major design decision we had to make was choosing the type of underground storage system we would use. We needed to make sure whatever we selected would satisfy all of our design criteria and also meet the village's expectations. First of all, the height and footprint of the detention facility were dictated by our site constraints, so the required 23 acre-feet of storage had to fit into the available space. The structure also needed to provide minimum HS20 loading because at some point the driver of a truck or an emergency vehicle might drive over the field without knowing what's been built underneath it. The village and the park district had agreed that use of the north ball field would only be lost for 1 season, so construction had to be completed in an 8-month construction window. The detention system would need to provide a long service life with a strong warranty. And finally, cost was very important. The village needed the construction cost of the underground detention to fit into their overall budget for the project. The village wanted the detention to drain by gravity so they wouldn't have to deal with operation and maintenance of a pump station. Therefore, the invert of the receiving storm sewer limited the maximum height of the storage vault to about 10 feet. Additionally, construction had to stay within the Park District's property and off the south ball field, leaving us with the construction limits shown in yellow. We developed an ideal detention footprint, which is shown as the gray box, and it allowed just enough space for excavation at a 1-to-1 slope, and also a small buffer around the base of the structure for workers. We considered 5 main types of underground storage systems for this project. The first one was Stormtrap's Double Trap product, which is a modular precast concrete system. This type of detention provides very efficient storage, which was important given our particular site constraints. In fact, about 93% of the total volume would be open and available for storage for our particular structure dimensions. We also considered corrugated metal pipe systems, which provide storage in circular pipe as well as the void space of the backfill. Those options offered some potential cost savings. However, the system provided less efficient storage than Stormtrap, making it a very tight fit for our site. And additionally, the village had some concerns about durability of CMP and also limitations of the warranties that came with the products we considered. Another option we looked at was an open chamber with a concrete slab roof supported by reinforced stone aggregate piers and walls, which would essentially be made up of stacked gabions. About 64% of the total structure volume was calculated to be available for storage, which wasn't going to work for our project. Cast-in-place concrete storage was another very efficient option, which offered a lot of design flexibility. However, it would have required structural engineering, and it was ultimately ruled out because the curing times wouldn't work with our 8-month construction window. And then finally, plastic and resin modular systems weren't good options for us because the products we looked at had height limitations, which didn't work with our design. After considering all of their options along with our input, the village decided to go with Stormtrap's Double Trap product for the underground storage vault because it was a perfect fit for the project needs. The system is made up of modular precast concrete units which can be configured into just about any footprint. The structure can be up to 11 foot 4 inches tall, which worked with our proposed height of 10 feet. The Stormtrap design allows for quick installations, and pieces provide very efficient storage, which minimize the overall footprint. The system doesn't rely on void space storage, which means that any sediment accumulation can be easily accessed and cleaned. And then finally, the 50-year warranty that Stormtrap provides really stood out from the other options we considered. In a minute, I'm going to play a short video showing a pretty basic rendering we put together prior to construction, which showed what the storm trap and restored ball field would look like after completion of the project. We used this at a public informational meeting to give residents a better understanding of the project and just the scale of the underground storage that was going to be installed. The village authorized Baxter and Woodman to move forward with the design of the rainwater harvesting system alternate in August of 2015 when the village's intergovernmental agreement with MWRD was being finalized. The concept of the design was to store water in the storm trap for reuse and then pump that water from the storm trap to the irrigation system. The system would also use available weather forecast data to automatically drain down the storm trap in advance of large storms, making sure that the full storage volume would be available for stormwater when it was needed the most. Because the Illinois Department of Public Health considers spray irrigation systems to be plumbing systems, they had to review the project and issue conditional approval. IDPH required that the irrigation system meet NSF 350 standards for water quality. They also required monthly testing for E. coli by an IEPA-approved lab for 1 year after startup. And also, irrigation hours had to be limited to the nighttime to avoid unnecessary exposure to people. Even though the water will be treated, it still won't be potable, and they don't want people being sprayed inadvertently or kids running through the sprinklers. The village continued to look for opportunities to use harvested water in other ways as we were progressing with our design, and they eventually asked us to add a spigot to the project, which could be used to fill tanks for watering plants and trees at other locations around the village, and for vac trucks and street sweepers as well. The Illinois Department of Public Health typically doesn't deal with requests to use harvested water off-site, so this complicated the approval process a little bit. We did eventually receive approval with additional conditions. They required installation of a locking mechanism on the spigot and non-threaded fittings so that it wouldn't be confused with the portable water source. And then once the water is taken off-site, IDPH won't allow any type of spray application. They will allow the village to use harvested water for vac trucks and street sweepers because they aren't sanitary equipment. One thing to note is that during our discussions about the project, IDPH expressed concern for potential cross-contamination among tanks, hoses, and any other equipment that would be used by the village for potable water sources or pesticides. However, avoiding cross-contamination will ultimately be the responsibility of the village, so that's just one extra thing to think about when planning a system like this. In order to meet IDPH's requirements for water quality, two major components were added to the design. The first is pretreatment filtration upstream of the storm trap, and the second was UV sanitization to treat water before pumping it to the irrigation system. Pretreatment filtration is provided upstream of the storm trap with a precast concrete chamber located in line with the inflow pipe. That chamber contains a filter which captures leaves, trash, and other floatable debris, and it also removes suspended solids and hydrocarbons. Filtration is important for the functionality of the rainwater harvesting system because it prevents clogging of the sanitization and irrigation equipment. Additionally, it reduces the frequency of maintenance required to clean debris and sediment from the bottom of the storm trap. Once the inflow water is filtered, it needs to be stored in the storm trap for reuse. Our original design concept was to install a gate or valve at the outflow pipe to hold back water. The main advantages of this type of a system would be it would require no modifications to the original storm trap design, and also the storm trap would drain entirely by gravity. However, the watertight sealing of the joints would be required over the full footprint of the storm trap, which we learned would be more expensive than anticipated. Additionally, the gate or valve would need to default to open in any sort of failure condition. So in the case of, for example, power loss, or if the water level sensors were giving back bad readings, we would need to find a solution that would default to open to make sure that all of the stormwater storage was available. We ended up ruling out this option, however, because the estimated construction costs wouldn't fit within our available budget. The second option we considered was to store approximately a half-acre foot behind a partition wall with outflow controlled by a gate or valve. Calculations showed us that half an acre foot of storage would provide about 1/8 of the required seasonal irrigation water without replenishment. Based on a study of past rainfall patterns, we determined this volume should be adequate to irrigate without ever needing to supplement the harvested water with a domestic water supply. The advantages of this design were that it reduced the watertight footprint required, lowering the cost from the original concept that I just discussed. However, the design would still require a gate or valve which defaults to open during failure, and more importantly, the partitioned area would fill up first, increasing tailwater elevations acting on the inflow pipe. We found this would increase upstream flood elevation for certain storms, which is not a good thing for a flood control project, and eventually we ended up ruling out this option as well. The third storage option we considered ended up being our final design. It provided approximately a half-acre foot of storage below the gravity outlet with a section of taller 11-foot 4-inch storm trap pieces. The advantages of this design were that it was the least expensive option and fit within our budget. The additional storage volume could also be made available for detention by draining it down in advance of large storms. And since the reuse volume would be bonus volume, failure conditions and weather prediction would not be critical to achieving the intended project benefits. The only major disadvantage of this design was that the storm trap would not drain by gravity, and a small pump would need to be added. In order to accommodate the rainwater harvesting system, the storm trap had to be divided into two subsections. The first being a sump area, which is 11 foot 4 inches in height and stores water for reuse, and then the remainder of the structure, which is 10 feet tall. Both of these areas are made up of modular units placed on an aggregate stone foundation. The total storage volume provided in the final design is 23.7 acre feet, and a total of 1,722 individual storm trap units were needed. Here's an isometric view of the storm trap configuration, which shows how the individual pieces fit together within the proposed detention footprint. And the shaded pieces shown on this plan view are the taller 11-foot 4-inch pieces where the sump storage volume is provided. This cross-section drawing shows the 11-foot 4-inch storm trap units for the sump in profile view next to the 10-foot pieces, which make up the remainder of the storm trap. I mentioned earlier that the project included storm sewer improvements which convey storm water from upstream areas to the storm trap. Storm water which infiltrates into the soil directly above the storm trap can flow into it directly through gaps at joints between the individual units. A 6-inch layer of aggregate stone was placed below the topsoil layer, which allows water to flow into these gaps more freely. And a geogrid and double layer of geotextile fabric were installed above each gap to prevent stone from falling into the storm trap. Additionally, another layer of geotextile fabric was installed above the aggregate layer to prevent topsoil from moving into the stone. Water is held in the sump area of the storm trap for reuse by adding a watertight seal along each joint to keep water from seeping into the soils below the storm trap floor. All joints in the sump area were sealed with Zypex patch and plug, which is a hydraulic cement compound that is high strength, fast setting, and also non-shrink. And then seal joints were tested following construction to ensure that there were no leaks. Before water can be pumped from the sump area of the storm trap to the irrigation system, it will pass through a UV sanitizing system. The system treats the water with UV bulbs, which kill bacteria and pathogens with radiation. And it also includes additional filters to remove suspended solids, which can reduce the effectiveness of the UV treatment. Advantages to UV treatment are that it requires minimal contact time, it's non-chemical, and also it doesn't produce any odor. Baxter and Woodman's control systems integration team developed automated controls for the rainwater harvesting system, which use online weather forecast data to pump stored water to the downstream sewer in advance of large storms. As I mentioned earlier, pumping out the stored water allows us to take advantage of additional storage volume provided in the sump. To do this, we used results from our XP-SWIM model to develop a conservative correlation between predicted rainfall depth and then the expected water elevations in the storm trap. Our touchpad control screen is located on site in a locking enclosure, which can be used to check on the system, adjust settings, view alarms, and shut down or start up the system. And also a web interface is available to monitor the system remotely. One big thing to take away from this project is that collaboration, negotiation, and public outreach can be critical for successfully completing a project which will benefit the entire community. In our case, the ideal location for detention was a park that was not owned by the village, which is a pretty common situation in densely populated areas like Northbrook, Illinois. When using a public open space for detention, underground storage is a great option to preserve or improve the current land use. For Wescott Park, storm trap was a great fit, and it helped us meet our project goals while also working within our site constraints. This project was a great example of opportunities which exist to incorporate green infrastructure into more typical stormwater projects. Not only were we able to fit a rainwater harvesting system pretty seamlessly into the framework of our original design, MWRD also partnered with the village, covering the added costs of those improvements. And lastly, technology exists which enables us to move beyond passive stormwater systems to maximize the benefits provided. For this project, we were able to use weather forecast data to have our reuse storage volume double as bonus stormwater retention. I think we'll be seeing more of these types of systems moving forward, including retrofits of existing detention basins, especially in areas where available space is hard to come by. I'm going to wrap up with just a few photos taken during construction, which was completed about 3 weeks ago, and then also a short video. The photo on the left shows excavation within the park to prepare for installation of the storm trap. And then on the right, you can see storm trap pieces, which were just delivered to the site, being moved and temporarily stored on site. Here you can see the preparation of the aggregate base layer before installation of the storm trap pieces. And here are a couple more views of the partially installed storm trap system taken by storm trap's on-site camera, which was actually present for the entire construction process. Here are a couple views inside the storm trap, and you can see there's some cool effects with the lighting coming from outside. These photos show precast junction chambers which were installed along the storm sewer route to equalize flow between the existing and proposed storm sewers, which were constructed in parallel. We didn't have enough cover over the storm trap to use typical concrete post foundations for the ball field's backstop and dugout fences. So the photo on the left shows spread footings we designed to support the posts on top of the storm trap. The photo on the right shows the restored infield and the installed backstop fencing. Here are a couple pictures of the water treatment enclosure and the controls as they were being fabricated. And then lastly, here are a couple photos of the restored park. All of the above ground equipment is shown on the left, which includes the water treatment enclosure, the rainwater harvesting system controls, and also the irrigation controls. And then finally, here's I'm going to show a time-lapse video of construction in the park from excavation all the way through restoration, and then ultimately the ribbon-cutting ceremony when the park was reopened. All right, and with that, I'm going to turn it back over to Bob.
Okay, thanks, Paul. Well, for the next few minutes, Paul and Kelly will respond to some of the questions that were submitted during the presentation. While they start that, you can continue to submit questions using the Ask a Question box on the left side of the webcast dashboard. So our first question is, can the storm trap be entered for maintenance purposes?
Yeah, I'll take that one. Access options, they can be customized with storm trap. For our project, we installed 2 4x4 hatches with ladders where people can enter the storm trap to clean it out or do any other maintenance that is necessary. I think just the only thing that you have to be aware of is that you have to work with storm trap to make sure that the structural integrity of the pieces will be maintained.
And the only other note I'll put in there is that it is a confined space as well, so you have to follow the parameters for entering the space prior to maintenance.
Okay. Does the field surface drainage rely solely on seepage through the joints of the storm trap top surface?
No, we actually installed several storm drains which are located outside the playing area of the ball field. The lids are all locked shut to prevent anyone from attempting to enter the storm trap at those locations. Okay,
next question. Why a watertight seal on the bottom? this prevents infiltration back to the groundwater?
Yeah, so the watertight seal was only used in the sump area of the storm trap, which was the volume of storage dedicated for reuse. The rest of the storm trap, we do allow infiltration in the soils. For the sump area, we wanted to hold that water in so that it could be used for irrigation.
Okay. Next question. What is the minimum cover required above the storm trap?
Minimum cover can vary depending on the site-specific conditions, but I understand that it's pretty typical to require about 6 inches to a foot to achieve HS20 loading capacity. That being said, storm trap can work with you if you have special design constraints or if you have different loading capacity criteria.
Does the response to weather forecasts require the operator intervention, or is it automated?
That's automated. So I think the system, it pulls available weather forecast data from an online source and then handles all that automatically.
So how is the system cleaned out?
I guess that sort of depends on which part of the system that you're talking about, if it's the storm trap or the water treatment equipment. I guess if it's the storm trap, I'll direct that question to the storm trap people.
Okay. Were there any issues or conflicts with underground utilities, such as lighting or drinking fountains, running between the top of the storm trap system and the ground surface?
We did have one drinking fountain on site, which we relocated as part of restoration of the park. I don't believe additionally there was an underdrain system that existed currently or previously throughout the ball field area. That system was removed and ended up being replaced with the infiltration into the storm trap roof that I discussed earlier.
Did the previous construction of the village take place in an identified FEMA 100-year flood zone?
No, it did not.
Okay. Let's see. Is the purpose of this to store water or to address flooding issues? The reason I'm asking is that we have a bridge that always gets flooded in rain, and I wonder if the method mentioned in the presentation can be used to mitigate the bridge flooding.
The primary was the flood control components that the project offered, and then the rainwater harvesting project was just an additional advantage that we identified during the process. But primarily a flood control project first, but the green sustainability is definitely a benefit that we realized at the end.
Did you need a heater inside the above-ground enclosures?
Yes, those are heated enclosures.
Did the village consider buying out some of the houses nearby to increase the usable area, to increase the amount of flood protection? In other words, to get closer to the 100-year storm?
One of the difficult parts in Northbrook is the property acquisition cost. The average residential house is roughly in the $650,000 range. So acquiring enough properties to put together to provide additional benefits becomes a costly endeavor prior to actually putting the improvements in.
Okay. What was the construction duration?
Construction began, I believe, in March and ended in the middle of November.
And were there any groundwater issues?
No, we had soil borings done in the park before construction, and they all indicated that the water table was well below the bottom of the storm trap.
Did you consider infiltration for this project?
I think kind of touched on this in one of the earlier questions, but yeah, water can infiltrate from the bottom of the storm trap. However, the soils in the park are mostly, the subsurface soils are mostly clay and don't allow a lot of infiltration.
You may have just answered this, but was dewatering necessary during construction or had to be considered in the design?
I think there were some instances where they had to deal with dewatering, yes.
Okay, this question is, I may have missed this information earlier, but what was the drainage area to the system from the surrounding neighborhood?
I don't have the exact number right now, but that's something I can follow up with following the webinar.
Okay. And can you please explain the UV treatment more? Was the UV only conducted on the pumped portion of the system when you want to use the water?
Right. So water is pumped from the sump storage area through the UV treatment enclosure before it gets pumped to the irrigation system. So yes, it's only the only water that's treated is the water that's being used.
How was the stormwater utility set up? By vote, property-related fee, et cetera, and how much per parcel? Did it fund this entire project?
So the Stormwater Utility Fund we're a home rule community, so the village implemented a stormwater fee on water consumption. It's $1 per 1,000 gallons consumed. So that is the funding source for all the village's stormwater operation maintenance of our systems, and then also pays for the debt service on the construction projects.
Is there an annual subscription for stormwater monitoring, and what type of cost is associated with that?
For the
I would go ahead, Kelly.
So that's referring to the SCADA system that monitors the pumping. That is something that the village has worked with Baxter Woodman on to monitor it. Eventually, the village will be able to log into that and pump down the sump pump area as storm events come up. So it's a web-based service.
And I think maybe to add to that is I believe the software is owned by the village and there is no subscription that's required. There's no annual fee for the software.
Did the project come in on budget?
Yes, it did.
Yeah, it came in under budget actually. I think the final construction cost was somewhere in the neighborhood of $9.68 million, I think.
Now that the new park is finished, has the village considered expanding the system to the other side of the park in order to get the 100-year storage?
In the initial discussions with the school district, at the time they were not interested in allowing the construction of the system underneath their property due to future expansion concerns with how that would play into the school in the future. So it has not been considered, nor at this time I think it would be entertained.
Speaking of the UV system, were there other sanitation devices that were considered aside from the UV system?
We honed in on the UV pretty early on. It was something that was recommended to us by a firm that has experience doing these types of systems, and no, we didn't really we didn't dig too deep into options that required chemicals or any chemical treatment or anything like that.
What percentage of the total project cost was devoted to the UV system?
The total cost for the rain harvesting system portion was $476,000.
Yeah, and that included the expansion of the storm trap to include the sump and then all the other additional components that went along with the UV system. So specifically the UV system, I would have to get back to you on that one. It's something we could probably post in the Q&A summary on the website.
was the 25-year storm event used as the design parameter? How many residences will be flooded with the 50-year event?
I believe that was sort of a result of the site constraints. The village wanted the detention system to drain by gravity, so we had a height limitation to the facility, and then also we had the footprint that we were working within. Based on the village's master plan study, they determined that they could get about 25-year protection for that. So that it was more of, for our part of the work, we were more confirming the 25-year protection, which was the best that they could do given the site constraints.
Let's go with one more question before we end up. Please explain the weather control system more. The weather control system only pumps the remaining half acre in the lower 1 foot 4 inches?
That's correct. So in advance of a large storm, so I think we have right now on the initial settings for the storm trap controls, if rainfall indicated that the expected elevation in the storm trap could exceed 50% of the total volume, then we would pump out that last half acre foot to give a little bit of additional stormwater storage.
Okay. So as we finish up, you can download your certificate of completion from the Event Resources section on the left side of the screen. After downloading the certificate, enter your name in it and print and save a copy of the PDF. The certificate will be available through the end of today only. A hard copy will not be mailed or emailed to you. If you missed our note at the beginning and you are watching the live webcast with a group on one person's computer, please download the multiple viewer registration form and complete and submit the form to receive credit. We need this information in case you are audited and we are contacted to verify this continuing education activity. Additionally, this webcast is being recorded and will be archived on csengineermag.com/continuing education. For viewers of archived webcasts, click on the quiz button at the bottom of your screen to take a quiz on the presentation. Archive viewers must pass a quiz in order to download a certificate of completion. Questions that were submitted but we didn't take the time to answer today will be available online within a few days at csengineermag.com/continuing education. So please check there for further discussion about today's topic. As we conclude, you should see a webcast evaluation survey. We appreciate your feedback, which helps the WAG Group and sponsors such as StormTrap plan future webcasts. So thank you to Paul Siegfried and Kelly Hamill and to everyone who joined us. This ends today's webcast.